Now, radioactivity discusses, or when we talk about different types of reactions between atoms, between different elements and things like that, there are basically two types of reactions. One is where the atoms are rearranged, but the identities stay the same. So if you're dealing with, for example, if you have two hydrogens plus one oxygen, this leads you to, there's a hydrogen, there's your oxygen. So you have two hydrogens plus one oxygen. It leads you to something called H2O. What's that called? That's water. So you have some hydrogens and an oxygen. They come together and they form a water molecule. Well, the thing is, in the water molecule, there's a hydrogen atom in there. And that hydrogen atom is exactly the same as it was before. It hasn't changed. It doesn't change its identity. There's another one of those, and the oxygen. Now, yeah, the electrons are bonding together, and they're coming together, and the forces are holding them in place. And the way that I kind of talk about this is, these are puzzle pieces that, when you put them together, makes a picture, but each individual puzzle piece doesn't change. But when we get into what we call nuclear reactions, when we're dealing with nuclear reactions, unstable atoms change by emitting what we call alpha, beta, and or gamma particles. The element changes into something new. And that's different than this type of reaction where you have just two hydrogens and an oxygen coming together. They lock up. We'll talk more about the forces involved with that and why they do what they do. And they become a brand new picture. They become a brand new molecule, but the individual atoms don't change. This is, you have an atom, it's unstable. And after that, it becomes something new. It becomes something different. And that's because it emits these radioactive particles. Now, first question is, do we all understand what emit means? Anybody not understand what emit means? So if I ask someone what emit means and I say your grade depends on it, you guys are all comfortable answering that question? All right, see. There are the hands. The hands are popping right up. Now, think of my sound bar here. As it is, the sound bar is nice and quiet. It's just a sound bar. But now, okay, it started to emit sound. So sound started to leave the sound bar and go off. That's what we're talking about by emit. And when you hear the word emission, basically what you're going to get is you have your nucleus, and then something pops off. And other things pop off. And that's what's going to happen when we're talking about it emits things. It's going to send things off in certain directions. So that's kind of like a layman's terms of talking about that. Now, back in the 1800s, long time ago, 1800s, they started talking about radiation. They started seeing that, all right, some of these crazy elements that we're finding are not very stable, and they're decaying, and they're emitting these weird particles, and these particles are affecting a lot of things around it. So they had a basic experiment, and here's the setup for the experiment. They start with a source. And this source is radioactive. And in front of the source, they'll put a big lead block. So this is lead. Anybody know why they would use lead? Well, one, it's stable. But lead is extremely dense. So what it would do is lead would block radiation. So the particles coming off, because it's so dense, it would block radiation. What they do, though, is they put a hole to let a little bit of the radiation come through. Then they put a plate up here, and that plate is positively charged. This plate down here, they'd put another plate is negatively charged. And they wanted to see, because when you're talking about stuff with atoms, you're talking about protons, neutrons, and electrons. And what type of charges are we talking about there? Proton has what type of charge? A positive charge. Neutron has it's neutral, so it has no charge. An electron has negative charge. Now, what they found out was the radiation that was able to go through the hole, part of it would go up here. Oh, and I forgot to put the last thing here. There's a screen that they would put here. And they'd have a zinc sulfide coated screen. So from the radiation that would be emitted from the source, it would go through the hole in the lead. It would be blocked otherwise, because you don't want a lot of that radiation coming out, because radiation is extremely dangerous to anything organic. So part of it was actually attracted to the positively charged plate. Another part was attracted down to the negatively charged plate. And something else was not affected by either plate. Now, what type do you think is attracted to the positively charged plate? Is it going to be positively charged, negatively charged, or not charged at all? Negative. You guys are right on with this. So we could say this is 1 minus. And this guy is actually called a beta particle. So that one's your beta. Your beta is your negative. Now, same way. Think about what charge would this particle have that would be attracted to the negative? Positive. It has a charge of 2+. And this guy is called alpha. So this is your alpha particle. This is your beta particle. and the one smack dab in the middle, what do you think the charge is on here? All right, yeah, 0 charge, because it's not affected by the positive or negative. And if it looks like it's drawn closer to the positive, that's only because of my bad drawing. It has 0 charge, and this is your gamma. So there's 3 types of radioactive particles: alpha, beta, gamma. And we want to go through and we want to talk about all 3 of them. So we're going to start with alpha. All right, but first off, any questions on the experiment? Yes?
How did you get the number? Why did 1 minus beta is 2 plus alpha?
They found that through a lot of experimentation that all the particles that were coming off that were negatively charged only had that. Basically, it's a 1 minus, which ends up being just an electron. That beta is essentially a single electron that's popping off. So it emits. If it emits just an electron, then you're getting. That's why you get the -1 charge from it. This guy ends up, the alpha one, which we'll talk about in a second. The alpha one actually has 2 protons and 2 neutrons. So your alpha particle, through a lot of experimentation with the different radioactive substances that they were dealing with, they found that the alpha particle that would always come off would be the same type of, the same particle. And it had the same materials in there. 2 protons, 2 neutrons. And what this ends up being is helium-4. And so the alpha particles, when you see helium-4 in any type of nuclear reaction, then you know it's an alpha particle. So if you see this, instantly you got to think, oh, that's alpha. That's got to be alpha. So these different ideas, it's the most mass between the 3. So because it has 2 protons and 2 neutrons, it has the most mass, because protons and neutrons have about the same amount of mass. So they have a ton of mass, and protons have a ton more than electrons, about 1,800 times more mass than an electron. So an electron is really, really tiny compared to a very, very big proton, even though they're all very, very tiny. If I confused you enough there. But like for right now, we're just kind of being able to identify basic ideas about these. Now, here's an example and of a nuclear reaction. Say you had 226, and then there's 88, and this guy is radium 226. And when we're dealing with chemical equations, this is basically like an equal sign. And when you read it, there's a left-hand side and a right-hand side. The left-hand side says, all this stuff on the left-hand side gets thrown together. This is what is the result of putting all this stuff together. Well, there's only one thing here, right? It's just radium-226. So if something by itself is undergoing a change like this, and that's what the chemical equations and the nuclear reactions kind of demonstrate, is some type of change is happening. If one thing is undergoing a change by itself, it's a nuclear reaction. So if you see one thing alone here, this is going to turn into 222, 86, and then it's going to be Rn, so it's going to be radon 222. So unlike water, which had hydrogen plus oxygen equals H2O, this ended up being the radium changed to radon 22 plus that helium 4, which is your alpha particle. So if you see this nuclear reaction, that should tell you that it has alpha radiation with it. And the alpha radiation, helium 4, is the key to that. Yes. All right. Because helium 4, which is right here, has a mass number of 4, which means that's protons plus neutrons, and protons of 2. So basically, since it emitted 2 protons were able to escape. It goes from 88 to 86. So that's where the 2 protons escaped from. And 2 neutrons escaped. So this number up here is protons plus neutrons. So it went from 226 to 222 because it had 2 protons. The 2 protons and then the 2 neutrons. But if you kind of look here, this represents 2 protons. 2 protons plus 2 neutrons. That's what that 4 represents. That 4 plus 222 gets you back to the 226. Good question. All right, now, beta particles. It has a 1 minus charge, which means it's 1 electron. So it has an electron that gets knocked off there. So it has mass, but it has only a tiny, tiny bit of mass. So it has, we'll say, a small amount of mass. And an example of this, 14,6 with a C. So this is carbon 14. And based on the nuclear reaction, it's going to become nitrogen 14. Yes, sir. That's charge. I forgot the G in charge. It happens. So it has a minus 1 or 1 minus charge, which means it has 1 electron. And now for the beta symbol looks like this. The nice thing is when you're trying to when you're looking at the nuclear reaction, basically from the equation you can tell. This guy's going to be your alpha because it has the helium 4 guy there. That's your alpha. Beta right here, because that's the symbol for beta. That makes it really, really, really simple for you because it means that's beta. So that'll tell you that there's a beta particle there. And as you can see, carbon 14 changed to nitrogen 14 because of all of this. Now, last but not least, there's gamma. There's your gamma particle. Now, there's some interesting stuff about gamma particles. Its symbol 0, 0, and it has the symbol for gamma, the Greek letter for gamma. That's what it'll end up looking like. It has no charge, no mass, which means it has no electrons, no protons, which would be what would give it mass, since it doesn't have any of it, because those things would have been attracted to the positive or negative plates in the experiment. It has high energy. When gamma radiation is present, it has a lot more energy than alpha particles. It has a lot more energy than beta particles. It is basically pure energy that comes off of it. And one of the things is, it is never alone. It comes with alpha or beta particles, or not at all. So when you have a gamma particle, it'll be accompanied with an alpha particle or a beta particle. And an example of an equation, nuclear reaction, that would show you 238, 92 uranium. So this is uranium 238, and it's going to undergo a nuclear reaction. It's going to have some radioactive decay going on here. It's going to become 234, 90. Then you get your TH there. It's thorium 234. Now, let's use some logic here. I lost 4 for my mass number. I lost 2 for my atomic number, which means I lost 2 protons, and I lost 2 neutrons. So what do you think, what type of radiation is going on here where you lose 2 protons and 2 electrons? Alpha. So you're going to get, from this guy right here, you're going to get alpha, but you also get gamma. So for this, you get an alpha particle that pops off, because that's what's changing it from uranium to thorium. And you have a lot of energy that's happening because of that as well, which means the gamma is associated with it as well. Yes?
Okay, so when you said it is never alone,
Yep.
then you say later on it'll find out that it doesn't have any alpha or beta particles at all.
Good question. Now, it's not alone because the element has to change, or the isotope has to change. Uranium 238 has to change to thorium 234, which means, it means that you have to lose some protons or electrons, or protons and electrons, whatever. So you have to lose something. You have to emit something out of that element. The only 2 types of radiation that have something to emit are alpha and beta. Gamma doesn't change anything. Gamma is just a release of energy. So the gamma itself, gamma radiation itself, doesn't change the identity of the original isotope. The only 2 that actually change it are the alpha and the beta particles. So, since we're going through this nuclear reaction, and we're going to end up with something different because of the radioactive decay, you need to have an alpha or a beta there with it. And there's still this energy that's being released, and that energy is the gamma radiation from it. So that's why gamma and alpha or gamma and beta are they get tied together, because you have to have that change in the original isotope. You have to change it from uranium to thorium. The only way to do that is to have some type of either alpha or beta radiation come off of it. So you need that to change the isotope, but the gamma is the energy that goes on from there. Does that make sense? Okay.
We could, like, instead of alpha, we could have used beta in the example, right?
Not in this example, because this is like a true example from nature. This is what happens in nature. If you have uranium-238, it will radioactively decay to thorium-234 with an alpha particle and a gamma. You can't just arbitrarily say beta and gamma. It has to actually happen for that particular isotope. So thankfully, a lot of scientists have done a lot of experiments, and they've been able to say, all right, when this is decaying, you're going to get an alpha, or you're going to get a beta, or you're going to get an alpha and gamma together. So they're all kind of set in stone what's happening. So in this case, you get an alpha and you get a gamma. You just can't say, though, beta and gamma and be done with it. You just can't throw them together. You actually have to go by what is actually happening. Not too bad, hopefully.